fins are also called, we call them as the ribs. Okay, and they are also called extended surfaces. These are the different names that are used to describe the fins. And firstly, why do we need fins? So I will talk about this one. And then some information about a simple fin here. So before starting about the fins, I will show the examples of the fins. Where do we have it? So the first example is in, that refrigerator. So in your refrigerator, you can see that there are lots of fins here. So for example, this one is a fin, a plate fin. This one is also a plate fin. So you can see the number of fins here. So you have 1, 2, so you have lots of fins here. Okay. And another the fin application is that, for example, for this heat exchanger, you can see these are the fins. In the form of a plate, you have the fin here. Also, I have also the fin here. So these are three-dimensional actually. So I'm showing only the view that we can see here. And the fins also you can see in the heating systems. So this one is the fin here. There's another fin here. Okay, so you have lots of fins. Or the engine. This one is the motorcycle engine here. You can see the fin. So you have one fin here, another fin, and also you have the fin here. You have the fin here. So also in cooling systems of the electronic components, you have the fins different. Also you have the fins here. You can see that this is the fin. Okay. And these fins. So if you look at this, the thermal analysis of the fins here that is shown, you can see the plate where it is attached. This one, for example, it is very hot. As you move along the fin, the temperature drops. So here you have the low temperature. Similarly here, if you look at the plate, it is attached. This one is hot temperature. But if you move along the fin here in that direction, you can see that the temperature of the fin is decreasing. So that here you have, for example, the temperatures are shown here. So here you have the 47 degrees Celsius. As you move along the fin and at the tip of the fin, so we have 28.6 degrees Celsius. So the temperature has dropped in the amount of 20 degrees Celsius. Similarly, here you can see the temperature values here. It is 25 here at the end, 25 degrees Celsius, but at the plate is 26 degrees Celsius. But this all depends on the dimension of the fins. If it is very high, if it is very small, okay, etc. And the material of the fin. So these are the fins that we are using, and you can also see different applications of the fin in real life. So if I go back to the first slide, and firstly I will ask this question: why do we need fins? Okay, to understand the meaning of the fins, so first let me write the convection equation. That Q dot convection, that's equal to that H, and you have the surface area, and you have Ts, and you have T infinity. Okay, and let's assume that we have a, that plate, something like this one. This one is hot plate. Okay, and we are trying to cool this hot plate. So this hot plate has a temperature of Ts, and there's an environment with a temperature of T infinity. And this environment, that tries to cool this hot plate with a coefficient of H. And let's say that this one environment is always, that is H. Okay. And with an H value, we are trying to cool this fin. So you cannot change this Ts value. It is not possible to change. You cannot change this T infinity value. These are fixed values. Okay, you cannot change it. What you can play with is that you can play with this H value. You can play with this surface area. How you can play with this H value? And the H of the convection is the function of velocity. Okay. For example, if you increase the velocity, so you can have the still air. For example, in still air, H, that is, H will be, that on the order of, let's say, 10. And if you have the wind, H may increase to, for example, 70, 80. And if you have, for example, if you install the fan, H you can increase to 150. Okay. These are all depending on the conditions that you have. This is the first option. You can play with H value. And the second option is that we can increase surface area. if you increase the surface area, you will have more heat transfer, and as you have more heat transfer, you can cool this device. You can cool this device easily. So that first option is that you are that increasing the AH value, and you are increasing the AS value. This increasing AS value is somewhat that easier method, and the easier and the cheaper method than the installing fan, because that in some places to install fan is impossible. Okay, so what you are doing is that you are increasing the surface area. This is the application of the fins. So I will give you just two examples for this one. So for the H example, it can be that. So if you are cooling your soup, okay, if you are cooling your soup, the first is that it can be in still air, so you let it cool, or so what you can do is that you can blow over the soup. If you blow over the soup, and then it will that cool easily. So this one is easy, faster. It will cool faster than when you let it that cool in still air. Or you can increase the surface area, and this one is the famous example for the glass of that cup of tea. If you are trying to cool the cup of tea, what you are doing is that you are trying to increase the surface area by putting it cup of tea. So you can put in okay, that's larger, okay, on a plate. So you can put your cup of tea on a plate, and it will cool that in a shorter amount of time. So these are the two famous applications that we are doing in our daily life. So this is the reason that we are using the fins. Okay, so how do we increase the surface area? You can see that this one was the first part, and now we have attached a fin. So now you can see that we have attached the fin on it. So you have increased the surface area, and this is the fin. And the shape of the fin is also important. We'll talk about in our next slides. The material of the fin is also very important. Which material are you using? These are two important stuff that we have to consider, and also spacing between fins is very important. So let me just write it here. So the first one is that the material. When I say the material here, I mean the conductivity K. Okay. And the second one is that, so if you have the spacing between the fins, this is also important. Okay. We'll see in next slides how it is important. And the material of the fin is also important, and the shape of it. Okay. Which fins are you using? You are using the rectangular fins or the circular fins, etc. These are all affecting the performance of your fins. Okay, so for the conductivity here, so the better one is that high conductivity material. So for example, it can be that aluminum, it can be copper. But between aluminum and the copper, we are choosing the cheaper one, which is the aluminum. Spacing between the fins, it is also important. If you have lots of fins installed, so I say that you have one fin here, you have another fin here, so that, let me go back to this part here. So if you install lots of fins, you have one here, and you have another fin here, you have one more fin here, so that this spacing will drop. If the spacing drops, if it drops, air suffocates. Okay. Air cannot end. For example, I have one more fin here. Say that. I have one more fin here. Okay. So that air cannot, that freely move between these fins. Okay. And therefore air suffocates, and that the H value drops. It is very similar to, you have the clothes, so that you have clothes here, you have cloth here, so wet clothes. So if you put, that the spacing between the clothes very small, so that the drying of the clothes will take lots of time. you will leave a lot of spacing, enough spacing here, I mean the enough spacing between the clothes, and that they will dry easily. So that the second one is the spacing, and the third one is the shape of it, and we will see next slide what are the shape of the fins. Okay, so another, that important stuff about the fins is that the place where it is attached. The fin here, for example, attached to this plate here, and this one is called the base. Okay. And the base plate. And when we say that the temperature of the base, so we mean that where the fin is attached, for example, on this base. And this part of the fin, part that you see here, it is called tip. It is a tip of the fin, and this part is the base of the fin. And the tip of the fin may be in different conditions. Okay, this part, for example, it can be insulated. Okay, you will see in next slides too. And it can be that there's convection. Okay, or it is also possible that the temperature of tip is given. Okay, so the temperature of the tip is given, and you can find the heat transfer for this fin here. And for using the fins or extended surfaces or ribs, we are using different approximations. Okay, I've listed the most often approximations here. The first famous approximation is that heat transfer is in one-dimensional in x direction, okay, and which is oriented towards the tip of the fin from the base since small thickness of AC. So let me go back to here. It is one-dimensional, and the heat transfer happens only in that direction. If it is x, if it is y, q dot y is approximately 0, but q dot x is dominant. Okay. So another one is that steady, that there is no temperature variation, no heat generation, constant K. The K of the material that you are using in the fin, this one, is constant. It doesn't change depending on the direction. For example, if you move in that direction, you will have the K. If you move in that direction, you will have the same K. The material properties are independent of the direction. So it means that the material is homogeneous. And the constant and uniform H, so that here for the fin, for example, if you look at the fin here, refrigerator fin. So what we are assuming is that we have the same H everywhere. For example, if I take the spacing between these two fins, I have H. And if I take this one, it is the same H and the same H. Okay. And independent of the orientation and the spacing, velocity, etc., we are assuming that it is the same H. Or you can see that this is the average H. In most of the books, it is shown as with H over bar here. Okay. And the cross-sectional area is sometimes constant for some simple fins. So we'll see that one. And this is the part that we analyze. Okay. And so I've said it, if H is suffocated at the base with more fins, less contact with area at the tips. This is also we have talked about. So it is possible that if you have let small spacing between the fins, and H may, so that air may suffocate, and you can have the drop in efficiency of the fins. But the assumptions that I've listed here are 6, but you can have all of the assumptions that are given by the Murray and the Gardner, so that there are 10 approximations here. So you can read them, and you can see that the analysis that we are doing is not so complex analysis. Okay. And these are the examples of the fins that I have shown to you. And we have said it, this one is the plate. And this is also called or heat sink. It is also called the heat sink because that, that if you cool it, this one is called that heat sink. Okay. And also you have the plate here and the etc. For example, you have the plate here. And the forms of the fins here, we have the annular or radial fins. You can see that it is, that installed on a cylindrical shape in radial directions. You have the radial directions here are, so that you have the R here. And this is the one example of the fins. Another one can be that straight fin and of uniform cross section. And this one is the attached plate here. This one is the plate, and the fin is straight. You can see it is the straight fin, and then uniform cross section. We'll talk about this one. You have the same straight fin, again attached the plate here. Therefore, it is called straight fin. And you have the non-uniform. So here the area is constant. So you have the rectangular area of this one everywhere. But here you can see that area decreases in the direction of the heat transfer of conduction. But this one is also, these are called the pin fins and the uniform cross section, and the pin fins are spans of non-uniform cross section. Okay. The uniform and the non-uniform. But for the analysis that we will do for the fin lectures is that always we will use the uniform analysis. We will look for the uniform analysis. The first one is that it is easy for solution. Okay, why it is, and the second one is that easy for solution, and you have the analytical solutions. Okay. The first thing is that it is easy, and you have the analytical solutions. Therefore, we will analyze the straight fins as well as the pin fins for our extended surface lectures. Okay, now let's analyze the resistance concept in this fin here in y direction, and then we'll analyze the resistance concept in x direction, and let's see in which direction the fin resistance is negligible. Okay, so first I will show the coordinates here. You have the x coordinate and you have the y coordinate. Okay, and for these coordinate systems, I will just write the dimensions of the fin. This dimension will be that L, and you will have one more dimension here. This will be the W, and you have the thickness of the fin here. Okay, and we are starting from the center. You can see that x coordinate is at the center, and for this fin, you will have the center here. You will have one. So the fin material here, this one is that's solid. So the fin is solid, and you have the air flowing over that fin. So you have the air that flows over that fin, and as well as below it. Okay, so here you have also the airflow. Below the fin, you have the airflow. Okay, and the resistance concept, if you look at from the cross section of it, so you have the fin here. Look at from the cross section. Okay. And I will show the same coordinates here. You will have this x coordinate and you will have this y coordinate. Okay. And here, if you have the temperature of T1, you will have one resistance here, and you will have another resistance here, and this temperature here will be T2 at the surface, and you will have this T infinity. Okay. Now, let's look at the resistance in first part. This one is the RCD, and this one is RCV or combined. The fin analysis, we are not considering the radiation. So let me just go back to here for the, I've listed the assumptions here, and we are not considering the radiation, but we are only considering the convection heat transfer for the fin analysis. Therefore, I will just write the CV. And the CD resistance, and that will be equal to the half of the, so let me just write the full equation, L by Ka. Okay. And the L here is that the thickness by 2 here. K is the conductivity of the material, and the A is the direction where you have the heat transfer. And that direction is that L into W. Okay. And the R of the CV is that 1 by H into A. Okay. And that one is 1 by L into W. This is the conduction heat transfer, that is the convection heat transfer resistances. So if I divide this RCD by RCV to see which resistance dominates, okay, if conduction dominates or convection dominates. To see that one, so I will divide these two resistances so that you can see that thickness by 2K and LW multiplied with this one will be the L and the W here, and you will have that thickness by 2 into K. And you can see that this thickness for fins is very small. So it can be, for example, 5 millimeters. It can be, for example, 3 millimeters. Even you can see the fins with a 1 millimeter. But if you look at the pictures here, these are, you know, that the larger views. If you look at the real application, you can see the thickness of the fin. It is very small. The thickness is very small. Here it is very small, and therefore the thickness is very small. And the K value here, conductivity, as I said in the previous slide, the conductivity, we want a material that conducts heat very good, because otherwise you cannot cool this one. Therefore we use aluminum or copper. So if you look at this one here, we are using aluminum or copper, because otherwise the plate here, it will not cool. Okay, and since the thickness is very small and the K is very high, it is very high for effective cooling. So how high? For example, it can be in the order of 200s. It depends on the application, but if you want a very good cooling, it can be 200s, or even you can see that K on the order of 20. It is also possible. Okay, and as you can see that thickness is very small, K value is very small. This number becomes very much smaller than 1. Okay, and what you see as a result is that the RCD, the conduction resistance in Y direction, is much smaller than RCV. Okay, and therefore we can neglect that the conduction in Y direction. Okay. Since the R direction resistance is much smaller than the convection around the fin here, so we can neglect the CD in Y direction. What happens is that you will have the dominant effect, which is the X direction, as we have said in the beginning of the lecture. You can do the similar analysis here and look for the resistance in X direction. And also you can look for compare the values of the CD and the CV. Okay, let me just do that for you one more time. And the RCD in X direction. Okay, in X direction here, for the heat transfer for X direction, again I'll use the same formula, which is the L by Ka, and the L value for this heat transfer is the L itself. You can see that it is the L. So if it is X direction, and for X direction thickness, you have the L value. So it will be L. So the L value is this one. Okay. So that, let me just note it. L is Lx. Let's put it. That clarified. For example, Lx. You can write it to not confuse it. Okay. And the Lx and divided by the area. The area will be that thickness of it. So you can see that T multiplied with the W. Thickness and multiplied with W. And the RCV will be the same RCV here. So you will have that 1 by, so you have also H here. So sorry, I have forgotten the H value. So you have the H value here. You have the H value and you have the H value. Okay. And the next is that RCV will be that 1 by H into area, which is L into W. So if I compare the RCD X by RCV, it will be equal to L x direction, t, and in the w, and also there is k here. Add the k value here. Okay, multiplied with k and divided by this one, it will be that h, l, and the w. And the w cancels out, and you can see that l squared and multiplied with h and divided by t and the k. So you can notice that, for example, so that if you assume, if, for example, h is in the order of k, but therefore h by k is in the order of 1. So this one is 1. Okay. For maximum, for extreme case. Okay. But it is not. In reality, it is small. It is smaller than 1. But you can now see that L squared by T is much, much greater than 1. So the conduction X direction you cannot neglect. So that CD in X direction. Therefore, for fins, so that RCV and RCD, that in X direction is important. Okay, and these ratios here, you have the RCD X by RCV, and these are called, this one is called Biot number. Okay, and this one is also here. This is called Biot number. So what is Biot number? Biot number shows resistance of that resistance that you neglect, shows ratio of actually. So it shows the ratio of the resistance that you want to neglect to resistance that you think it is dominant. Okay, it is the ratio of the resistance that you want to neglect. For example, for this case, you can't neglect it. Okay, and for this one, you can neglect it. So you can see that here, Biot number is much smaller than 1. Okay, so therefore you can neglect the resistance in CD Y direction. Okay, but here Biot number is greater than 1. Okay, therefore can't neglect. So in general, if Biot number is smaller than and equal to 0.1, so can neglect. Okay, and this is the, okay, now comes the final one, which is the Finn equation. Okay. This is the Finn equation that we will use, and the Finn equation is given as this one. The temperature squared, so that second order derivative of temperature minus Hv by Kac, and multiplied with T minus T infinity is 0. This is the Finn equation, differential equation. This one is second order, and the linear differential equation. Okay. And to solve this differential equation, this one is also non-homogeneous. Okay. And the first, how did we derive it? I will not, fully derive it, but I will show how they have done it. So that to derive it, what you will do is that you take a small cross section on this fin. So that one is that one. So you will take a small cross section on that fin. This is the cross section that you will take. Okay. And for that small cross section, so this will be the x coordinate, and this one will have a thickness of del x. Okay, and you will write the first law of thermodynamics. If you write the first law, and you will see that for that, so if I show the cross section here, this is the cross section, and this is the where you have the x coordinate, and into that cross section you have the conduction, which is Qx CD. You have the conduction out of the system, which is Qx plus del x, again CD, and you have also the convection, because you know that the air flows around it, and cools this system. So that here you will have that Q dot Cv. Okay. And this one is the same Q dot. If you write the first law of thermodynamics, what you will have is that steady case, you will have that in is same as out. And in that case, Q dot X will be equal to Q dot X plus del X and plus Q dot Cv. Okay. And you will write the equation, for example, for Cv, it will be HAS and the T minus T infinity. And for that Q dot X, you will just write Ka and dt by dx, delta T by delta X. Okay. You will just write these equations and simplify it. At the end, you will see this final equation here, which is that Finn equation. And to solve that Finn equation, so we will need some, so to solve it, so if I give you just one example, say that the temperature change with respect to X is 5, okay? And to find the change of temperature, it will be that 5X plus C1. You have a constant here, okay? And to solve it, or to find this constant of C1, what we need is that we need boundary condition. Okay, if you have the boundary condition means that the value of a function at a location. So in most of the case, this location is the boundary, or it is beginning or the end. Therefore, we call it as the boundary condition. So therefore, to find this temperature here, we need some boundary condition. For example, if I say that the temperature at X is 0 is 0. Okay? And therefore, you just replace it value here, and you will see that temperature at 0 is 0, so that you will have 0 will be equal to 0 plus C1. And from here, C1 is 0. You can see, I've just given you one location where X is 0, and you have found the C1 value. And the problem here was that this one is first order. And since it is first order, I needed one boundary condition. So for first order, one boundary condition is enough. But for the equation that we are having here, it is the second order. So that d squared T by dx squared minus hp by kac and T minus T infinity 0. It is second order. Since it is second order, you can see the order of the equation. So we need two boundary conditions. Okay. And to find you will have two boundary conditions to find C1 and the C2. Okay. And to find these boundary conditions of the C1 and the C2, so sorry, the C1 and the C2, we need boundary conditions. And the boundary conditions will be that, so that it will be, let me add this one and then look at the table. These boundary conditions, it will be given at boundaries. The name says it, okay, or locations. That location will be when X is 0. This will be the first location. And the second location will be when X is L. When X is 0, you can see the X coordinate here. This is the X coordinate that you move in that direction. You can see X coordinate. X0 means that the base. Okay. This one will be base. And the X is L, the length of this fin here. And it means that it is the tip. This one is the tip here. Okay, we need boundary conditions for the base, and we need boundary conditions for the tip. For these boundary conditions for given, for example, it can say that the base temperature is 5 degrees, or it can give the conditions at the tip, which conditions dominate at the tip. And for this, the case of the boundary conditions, we have 4 types of fin problems. Okay, we have 4 types of the fin problems that are given according to these boundary conditions here. And let's see the types of the fin problems. The first type of the fin problem is that, so let's start from the easiest one. And the easiest one, actually the first one is the easiest one. The base boundary condition, you can see the temperature at the base is always given. In all of these 4 type of problems, you can see 4 types of problems. This one is the 1, this one is 2, and the 3, and you can have the 4. The temperature of the base is given. Now the temperature boundary condition at the tip, here, the boundary condition at the tip, it may have different conditions here. And here we have shown the theta, and the theta means the temperature minus T infinity. Okay, so this one means, let me show that here. So that theta means T minus T infinity. Okay. If I say that the theta tip means that the temperature at the tip minus temperature of the infinity. Okay, so that is what we mean by the theta. Okay, the first one is that the theta tip is 0, or in other words, the T of the temperature of the tip is equal to T infinity. This is the first case. And if you have that case, the temperature distribution is given as like this one, and the heat transfer rate from the fin is m. And the m is this one, HPKSE under square root into theta base. And the base is that, I will just put the base here, and the base here, I will have this function here. This is the first case. And if I ask you this question, and to see who knows the answer, when do we have the tip temperature same as the T infinity? So let me just go back to here, show you a clean slide here. So the temperature here, for example, is 70 degrees Celsius. And the environmental temperature is, for example, 20 degrees Celsius. Here you have the tip. Okay. When it is possible that the temperature of the tip is the T infinity, same temperature as the environment. So you have the first condition is that the tip temperature is same as the infinity. Okay, and this is true for that is infinitely long fin. Okay, and in that case, you can find the temperature variation with this function here and with that function here. And the second case is that the tip temperature is given. You can see that the theta tip is theta given. So it is given temperature value. Let me just go back to here. For example, for this fin tip, I can say that the tip temperature is, for example, 25 degrees Celsius. Okay, and for this kind of the problems, that we can solve the temperature variation along the fin by this function and the heat transfer rate from the fin by this function. Okay, and another option is that this one is convection. Sorry, that the temperature at tip is given. Okay. Temperature at the base is always given. We are looking for the second condition that may help to solve this differential equation. Okay. And the third method is that the temperature doesn't change at the tip. When it is possible that the temperature at the tip doesn't change. Okay, so this one is possible when you have the insulation of the tip. So if you insulate the tip here, so if you go back to here, if you insulate it, so you will not have the heat transfer in that direction. If you don't have the, for example, if I just go back to here, if you have the insulation, Q dot by conduction will be 0. What was the equation for Q dot? Ka and the dt by dx is 0. K and A, these are constants, therefore the dt by dx is 0. This one is for insulation. Okay. Similarly here, if you have the insulation of the tip, you will have this one is 0. Or it is also called that adiabatic tip. And the last option is that you may have at the tip that Q dot by CV, this one is that CV, will be equal to Q dot by CD. This one is the conduction. Okay, at the tip, so this is the last option that you will have that heat transfer by the convection will be equal to heat transfer by conduction. If you remember from our previous lectures, if I take the interface And the interface means that it doesn't have any volume. So if you have the q.cd into that interface, that cd will be exactly the same as q.cv from that interface. Okay, this is the last option, and this option called this convection tip. Okay, and these are the options that you will have for the different types of the fin problems. And for the okay, now there is a graph for the adiabatic tip, and the graph is the temperature drop of the fin versus the ml. What is m? M is hp by ksc square root, and the l is the length of the fin. So l is this one, length of the fin, and the m is fin constant. Okay. If you look at the graph, and you can see that in the first case, when ml is 0.1, the temperature drop across the fin is actually the ratio. This one will be the temperature ratio. Temperature ratio across the fin is 1. So what it means, let me just show this case and the last one. Say that I have a plate, and on that plate I have installed some fin. Okay, the plate temperature here is the base. Let me just show you the base temperature here. For example, it is 70 degrees Celsius. Okay, and the base temperature drops in this manner, and at the end of the fin tip, for example, you have, let me don't show it on the graph here because it will create confusion, so that this one is the x-axis, and I will show the temperature versus in x-axis, and this is the end. Raise that one more time. Okay, and this one is L. At the beginning you start with T base. As you move along the fin, the temperature drops in that way, exponential way. It is also possible that the temperature drops in this way, and it is also possible that temperature remains in that way. Okay, temperature of the base, and the first one that is given here, it is ideal fin. Okay, and this one is that, you know, that it is not good. Why the first one is the ideal fin? Because it has the maximum conductivity. This one has the maximum conductivity, or the K. Because you can see that if the temperature here is 75 degrees Celsius, it is, you know, that sent here 75 degrees Celsius, 75 degrees Celsius, 75 degrees Celsius. You can see that information, the conductivity, information is propagated very fast. The temperature everywhere is 75 degrees Celsius. What it means is that it is K is very large. K is infinite. Okay, but if you look for the bad case where you have the temperature variation drops suddenly. Okay, so here, for example, you have the 75 degrees Celsius, but when you reach this location, the temperature is, for example, 20 degrees Celsius. It is not a good fin. Why? Because the fin has a resistance. What we want from the fins is that fin should have minimum resistance. Okay, but the fin here that you have here, this one has the maximum resistance, and this one has the minimum resistance. Okay, therefore the ML for the adiabatic fin determines whether it has good conduction or not. Okay, there are also different tables that you can use to solve the fin problems here. So you have the fin table 3.3, and you have the charts here, figure 3.43, and you have 3.44, which is the chart here that you can use. And it is also possible that, you know, that this one is equation 4. That is the convective tip. and you can convert it into adiabatic tip. Okay, how we can convert it? You can convert it by L corrected of the fin will be equal to L plus AC of the tip divided by the perimeter of the tip. If you do that correction, you can analyze this one. Actually, here it was convection. Now it is here is insulation. Okay, you can convert the convected tip fin problem to insulation fin problem and analyze it as the adiabatic way. Why? Because this one is easy equation, and this one is that hard, that difficult equation. And therefore, what we want is that easy method to solve the problem. That easy method is that we can take these corrected lengths, add it to the lengths here, and convert the problem of the convected tip to adiabatic tip. So before moving on to this question, I should give the small information about this problem. And here you can see that we have a spoon here that is inside the hot water, and the spoon part here, it is 100 degrees Celsius. Okay, and the question is that to find the temperature at the tip. You can see that this is a fin. So for that fin, for example, for this spoon, you have the temperature here, so some part of it inside the water. Here temperature is 100 degrees Celsius, and the here temperature is required to find. Okay, and this one is a fin problem. You have the base, you have the tip, and we can analyze it as a fin. But the problem that we are going to solve is that the turbine, so this is the turbine, and the turbine blades are attached to a rotating surface, something like this one. And for this rotating surface, the base temperature is 380 degrees Celsius. The base that they are attached, this one, is 380 degrees Celsius. And there is a, that the hot gas, because the turbine, that this is gas turbine. And the gas turbine in airplane, for example, I can give you just example in airplane. You have the turbine in airplane that uses the hot gases from the air and as well as the kerosene, the fuel that is burned. And we have this power of the turbine that gives you electricity that you are using in the airplane, or the thrust for the airplane. Anyway, you have the base, which is at 380 degrees Celsius, as well as you have the hot gases, T hot, which is 1000 degrees Celsius. Okay. And the convection coefficient of the hot gases is 350 watts per meter square Celsius. Conductivity of these plates, so this K value is 20. You can see that K value is here low. The reason is that you cannot use aluminum or copper here. That is the reason. You have to know that you have to take a material that is durable under this temperature. Therefore, you are having this low temperature of the material, low conductivity of the material. And the length of the blades is given as 51 millimeters. So this is the length that you are going to have, 51 millimeters. And the cross-sectional area is 5.9 centimeters squared. This is the cross-sectional area. You can see it is in the shape of the airfoil. These are in the shape of the airfoil. The reason is that you can have better lift force so that it can rotate easily. So that this cross-sectional area AC is 5.9 centimeters squared, and the perimeter of this material is of this blade is 110 millimeters. The perimeter is this one. Let me just show the perimeter to you. Okay, and this is the perimeter, the length of this circumference here, and this is 110 millimeters. And the base temperature is 380, as I said it. Determine the heat transfer rate, so that heat transfer rate from the gas to these plates. This is the first one. Second one is that what is the temperature at the tip? So that which temperature you are going to have at the tip here. So that T temperature of the tip. So that is another question that you should answer for this one. Okay, now let's solve it. So first thing is that we should identify the type of the fin. The first step, we should identify the type of fin. If I go back to here, so that we have 4 types of the fin. The first type is that infinitely long. The second type is that temperature at tip is given, insulation, and convection. So it is not infinitely long fin. So if I go back to here, it is not infinitely long. That first type, so that L is not, that infinite. So the first type goes away. Okay? It is not infinitely long. Now let's see the second type. Second type says that the temperature at the tip is given. The temperature at the tip is given. If I go back to this question, the temperature at the tip is not given. Actually, it asks for me. Therefore, it is not the second type. Temperature tip is not given. Okay. Now comes the third and the fourth options. The third option is that adiabatic tip. It is not adiabatic tip. And if I go back to here, if you look at it, it is not adiabatic. Okay, and if I go back to the last option, which is that convected tip, which is the case for our problem. It is convected tip. But the funny thing is that whether you take adiabatic tip or the convective tip, the results will be the same. Will be that very similar. The reason for that one is that the results will be similar is that because that since that the cross-sectional area of the tip is very small. Since the cross-sectional area of the tip, this one is small, we can assume this one as adiabatic tip, but we will not do it. We'll use the real case, which is the convective tip case. But you can solve by yourself with the adiabatic assumption. You will see that you have got the same results, similar results, because the cross-sectional area of the tip is very small. Okay. Now let's solve the problem here to see what's going on. First, I will find the heat transfer rate. So let's go back to the equation here. The equation says that firstly, I should find this capital case M, which is that H perimeter, P is perimeter here. K and the AC and the theta base is T base minus T infinity, multiplied with sinh ml and the cosh ml and the same cosh and the sinh ml. So what is cosh and the sin H? I have not said to you. And the cosh, sin H, tan or tan H. So these are hyperbolic functions. Okay. And the hyperbolic functions is that carry similar, that characteristic as the sine function, cosine function, and the tan function. They carry similar characteristics. For example, the d sine h by dx is cosine cosh d, for example, cosh by dx is negative sine h. So you can see that they have the similar characteristics. This is the first case, and the second case is that they are hyperbola. So you have to remember this part. And for the cosh, this function is the short name. This is the short name to the function of e to the power of x plus e to the power of negative x by 2. And this one, sine h, this one is the short name for e to the power of x minus e to the power of negative x by 2. For these ones, you can use any calculator. So the scientific calculators will solve this cosh, sine h, and the tangent. Okay, let me go back to here. You will find the sine h m into L, and the m is given as hp by KIC under square root, and the L is the length of it, and the h by mk. So you can see all of the rest of the values are the properties of the material. Okay, so I stop the lecture here. If you have any questions, you can ask. Otherwise, I stop the recording, and I will take the attendance. Okay, stop recording.